So, to sum up then, everything that we've learned here, I'd like to encapsulate it all in terms of a single physical hypothesis that summarizes all of the experimental information that we've seen so far. And the name of this hypothesis is something known as the de Broglie hypothesis. Now, de Broglie didn't quite formulate it this way, but it really is, he really deserves the credit for it. But I just want to frame it in a way that then later we can begin to build a formal theory about it. And there are really 5 key ingredients to the de Broglie hypothesis. But what we are saying in the de Broglie hypothesis is the following, and that is that the detection of microscopic entities, and these entities, of course, could be, our favorite, they could be electrons, they could be photons, right? They could be nuclei, right? It seems to be extremely general, right? The detection of these, right, occur, or the detection of microscopic entities occur as, number 1, discrete events, right? We certainly know from Millikan, for example, that the electrons always come in discrete units. And we know from the from the photoelectric effect that the photons occur as discrete units. And as I've said, the nuclei, their corresponding experiments, they behave sort of just like the electrons. So that's the first thing. They're discrete events. But not only are they discrete events, they occur as discrete events at, and the second key thing is random locations, and I can, name the location of a detection event. I'll call that X. And we know that they are random, right? We saw this in the G.I. Taylor experiment with the photons, because they have to, without knowledge of where each other has landed, they have to build up an overall continuous pattern. And G.P. Thompson found exactly that same thing with the electrons. And the only way to put those two things together, the fact that they're statistically independent and they build up a pattern, is to have them arriving at random locations, but according to, right, they have to be random, but they have to be following also according to a probability distribution Okay, now this probability distribution, which I can call P of X, so they're random, occurring according to a probability distribution. But the key thing about this probability distribution is we know how to compute it. That can be calculated right as, this is a key thing, 3, a superposition of waves. And again, we have direct knowledge that we can do that, right? Because certainly for the photons, they fit the classical interference pattern that is all you've been taught how to calculate as a superposition of waves. That's where those patterns were first studied. But we also saw, again, in the G.P. Thompson experiment, that in fact the electrons also seem to be, their probabilities are described by the same exact superposition of waves. And we've also seen now by tracking the classical trajectories that in fact a superposition of waves can track a classical trajectory. So that seems to be holding true for electrons just as well as photons. Now, there's details of these waves. To superpose them, you need to know two things about them. You need to know their wavelengths as a superposition of waves of wavelength. And for the electrons, we had direct measurements, right? That lambda equals h over p. Now, here's the cool thing that makes you really think that we're onto something fundamental that applies not only to electrons and nuclei, right, but also to photons. Because notice, if we go all the way to the beginning here, for photons, we've always had this that the momentum is the energy in the packet h nu over c. But you might remember your wave physics, right? Nu over c, right, is actually 1 over lambda, right? Because c equals nu times lambda. So then nu over c, which is what the factor you have here, would be just 1 over lambda. But if P equals h over lambda, that implies that for photons, lambda would equal h over P. So everything is becoming unified now with this one key relation for lambda. Now, if we go all the way back down to our hypothesis, so we've seen this works for photons and electrons, and as I've said, there's experimental data for the other microscopic entities. So we need to know, though, not just the wave length, but we also need to know the frequency. So if wavelength lambda, that was the fourth ingredient, and finally, we need to know the frequency, and frequency given by... And we just saw that for the electrons, h, the energy of the electron, the Hamiltonian, written in terms of momentum, the Hamiltonian has to match h times nu. But once again, this is exactly the relation for the photon, right? As long as we realize E equals h nu, that E corresponds to the Hamiltonian for our photon, because it just represents the total energy of the particle. So we've now managed to unify all of our experimental observations with one beautiful underlying hypothesis. So now what we're going to do in the course is we're going to think through carefully some more of the qualitative implications of this hypothesis and even begin to get kind of semi-quantitative. We're not quite going to construct a formal theory from this hypothesis yet. We need to build up some intuition about it before we can really formalize things. But nonetheless, you'll see there's quite a lot we can do with this. And then finally, we will build that formal theory and we will come back and confirm all of the types of analyses that we do at a semi-quantitative level, as we will be doing in the next few lectures.